Hello, and welcome to the next What the Hectagon video. It's been a couple of days. I've actually been spending a lot of my time reading... Whoa! What the heck?
Tagon.
Yikes. I've actually been spending a lot of my time reading through the books that I said that I got from Princeton Science Library. A while ago, the first one I got was the Gamma one, right? And I finished that a long time ago. Then I went through and marked off all the pages of interesting maths that I want to cover for this channel, and then I read the book on E, only a couple. This is more of a history book about the math, so not much new stuff that I didn't know or that I didn't want to share in this, but there's a very, very interesting way to arrive at the answer for the areas under polynomials that sort of is a precursor to calculus that I'm going to share pretty soon. I think that's lovely. And then I recently just sped through this book. I think I probably read this book in a couple of days, something like just over 200 pages, marked off all the really interesting stuff that I want to cover all about I. There's so much stuff that I just didn't, you just don't know because it doesn't get covered in a timely manner, or it can't be covered in a timely manner in classes or anything. And so I love books like this that sort of just dig in and shed light on all the beautiful mathematical facts. And so there's so much that I want to cover in this book. And so I finished those three, and now it's on to the larger monster of all of them, is Dr. Euler's fabulous formula cures many mathematical ills, also by Paul Nahin, I don't know, who wrote The Imaginary Tale. This comes after that. I haven't actually started reading it yet, but I'm very excited to get into it. It's the last of the four. I've already finished the rest of them. And that's all I wanted to mention about that. Today we're going to get into something that I haven't continued since near the beginning of when I started this YouTube channel, which is graphing particular functions. And I know that seems rather elementary, but I think it's enlightening to talk about especially functions that don't lend themselves to being quite so obvious as to where they are in the graph, why they have that particular domain and range. And ooh, I have an ear pod and I didn't even realize. So we're going to be covering the inverse trigonometric functions today. I'm going to explain why their domains and ranges are what they are, all six of them, and then in the next video involving graphing functions, we're going to graph the hyperbolic functions, and then I'm going to do the inverse hyperbolic functions after that. And then following those videos, I'm going to go over how to derive the logarithmic form for the inverse trig and hyperbolic functions. Those will probably be two different videos. Point is, this video is about inverse trigonometric functions like the arc sine, arc cosine, etc. And we're just going to cover all six, see what they look like graphed together, and then we'll call it a day. Okay, so how we're going to determine the domain and range of the different inverse trigonometric functions. Before we do that, I want to consider something. So recall the graph of y equals x squared, right? So y equals x squared. It's a parabola, right? And it infinitely increases to the left and to the right. Drew it in the way there, whatever. There you go, sorry, wasn't looking up at the camera. But this is a perfectly well-defined function in that every single input on the x-axis maps to one and only one output. And so therefore it is a function. A graph that is not a function is a perfectly valid graph, like a circle, right? It has two outputs for every input except the ones at the end. The thing that's necessary to consider with repeated inputs and outputs would be the inverse of this function, though, because the way we classify functions is they satisfy the vertical line test, right? In a very basic sense, if you could drop any vertical line anywhere over the entire function's domain and it will only ever hit one point of the function. But imagine we wanted to invert this parabola, which is to say flip it over the line y equals x, thus swapping all of the x and y coordinates, and therefore we get the graph telling us if I give you the square, what was the number that got me there, as in what is the square root of the number, right? So when you flip it, it's going to look like this. I guess I'll use a different color. It's going to flip right around the line y equals x there. But given what I just said about the vertical line test, you can see that there's immediately a problem, right? There are two square roots for every number, right? A positive and a negative solution, which means each input from 0 onward, that's the domain of the function in the real numbers at least, is not properly defined, right? Because there's two equally valid outputs for every input. And so what we have to do when we want to try and define or figure out if a function is invertible in the sense that just inverting it gives us a perfectly defined function, we want to know if it passes the horizontal line test, which is to say, does it intersect itself more than once with a horizontal line? And it does, right? And the reason we want to consider that is because when we then invert the function, that horizontal line becomes a vertical line. So the inverse function will fail the vertical line test. And so essentially the way we get around that is if we only want to get one value out, we have to restrict the domain of the original function. That is, cut off some of the original parabola y equals x squared. And because positive is generally the default position, it's merely convention to say take x to only be greater than or equal to 0 and ignore the negative part. So if we ignore the negative branch of the parabola, clearly this isn't going to go back up, right? So it's going to pass the horizontal and vertical line test, which means when we just invert this, we only end up with the positive branch, which means it no longer fails the vertical line test when we invert it. So essentially we can get a well-defined inverse function by restricting the domain of the original function, and that's all I wanted to say about that, because now we're going to do that with trigonometric functions, and we're going to see what's the most convenient way to define inverses. Because you'll notice, we could have just as easily said, take away the positive branch, inverted it, and then we would have ended up with the part down here just by default, and that would have been perfectly fine. All of our math would still be just fine. So let's see what happens when we consider trigonometric functions. So we'll take a look at sine first. If we look at sine, we know that it repeats the same pattern forever and ever, because it's an oscillating function. Notice this passes the vertical line test, because it's a perfectly well-defined function, but it fails the horizontal line test an infinite number of times if you just place the horizontal line between -1 and 1. Right, y equals -1 and y equals 1, it will fail the horizontal line test infinitely many times. Which means if we were to invert this function, we would just end up with an infinitely tall wave going like that, right? And if you do that on Desmos, if you say sine of y equals x, so inverting which one is the dependent and independent variable, you will end up with a wave that's just going like that up the y-axis. But if you put in the inverse sine function, you won't get that. You'll get a small portion of the wave. Best we can do is, because this is a oscillating function that repeats every 2 pi, right? Every about 6.28. Every 2 pi slice of it looks identical. So we want to sort of just hone in on one period of the function and define the inverse based on that. But we have to pick an interval such that we're not including any parts of the function that go back down on themselves so that it can, or back up, so that it can fail the horizontal line test. We want to, so it has to be somehow within, the interval has to be less than or equal to 2 pi, right? We have to constrain it in that way to get a single output for the inverse function. But we should also strive to minimize the size of the angle, the absolute value of the angle away from the origin, right? It would make most sense to just have the function defined close to the origin just for the sake of convenience, because we can pick any interval that is well defined, but it would just get inverted like up here or down here, so it makes sense to just keep the function right here, which is exactly what we're going to do. So as you can see, the best way to keep it, close to the origin and not bending back on itself is to restrict it from those 2 points there. So we're going to restrict the domain from -pi/2, because that's when sine is -1, to +pi/2, which is where sine is 1. Notice if I go any farther, it starts to bend back down, which means the horizontal line test will fail at those points. So we're literally stopping at the exact bottom of the trough and the top of the peak, right? So we're restricting that domain, and then we're going to invert the function based on that. We're going to reflect it across the line y equals x. And you're going to see that the domains and range of this restriction will flip. Right now the domain of this function is -pi/2 to pi/2, and by restricting I mean we're literally getting rid of the function, the rest of the function. We're just ignoring it as just a declaration, right? So the domain is going, which is -pi/2 to pi/2, and the range is -1 to 1, those are going to flip, and we're going to end up with the graph, which will look almost identical because it's pretty close. You're essentially going to end up with that graph right there. And it's not going past that, right? We're just inverting it. I hope that's clear. I'm going to erase the one that we currently have, the sine function, and we'll just see the, here, I'll just draw it in purple so it's easier to see. It just goes like that, and now it's going from -1 to 1. It goes up from -pi/2 to pi/2. Right? And so that's the inverse sine function. It doesn't really bend back on itself like I just drew that. It looks like that. And this makes sense because now we've restricted it to, well, what are the angles -pi/2 to pi/2? It's the right half of the unit circle. If you start at theta equals 0, you can go down to negative pi over 2, or you can go up to pi over 2. So it's the right half of the unit circle, not having done any full rotations yet. So you're starting at 0 degrees, or 0 radians. And the inverse cosine is going to work much the same way. So if we have the inverse cosine, we want to just employ the same thought process. It doesn't fail the horizontal line test while minimizing theta, if we can help it, or x, or whatever represents the angle. And so the cosine does this, right, like that. It's symmetric about the origin. And so we can't do like what we did with the sine function and pick a symmetric interval, because a symmetric interval for the cosine is always going to fail the horizontal line test because it's reflective. So it'll go, if it goes down on the left, it goes down on the right, which means there will always be 2 points that cause a problem. So the only way to restrict it is to go from 0 to pi. The only way to restrict it that makes the most sense and minimizes theta, while also picking the positive option, right? So if we could just as easily do negative pi to 0, but now we're not picking negative numbers. And so we inverted about this, and so we have to flip it up like that, and I will erase cosine. So yeah, we're erasing all the stuff we're not using, right? We're going from 0 to pi, and we reflect it over the line y equals x. And we end up with, which goes from -1 to 1, and from a height of 0 to pi, right? So these are the two inverse functions of sine and cosine. They're rather tiny, and notice this is going from 0 to pi. Which part of the circle is that? That's from 0 radians to pi radians. So the arc cosine graph, as it's called, is defined over the top half of the unit circle. So this is the inverse cosine, sometimes written like that. This is not 1 over the cosine. This is the inverse of the cosine function, sometimes also written as arc cosine of x. And likewise, this is the inverse sine of x, also known as the arc sine of x. Okay, so that's how you graph these two functions. They're quite restricted, but I hope it's clear why we're just motivating ourselves to do the most efficient work and the smallest intervals, right? So we're trying to be pragmatic here. Next, we go on to the secant and cosecant functions. This one's a little interesting because it's got infinitely many infinite discontinuities, and so we have to again try and pick the smallest part, right? The smallest closest to the middle, and it's actually probably going to heavily depend on our decision of the intervals for sine and cosine. So, because we want those to be related somehow, right? We don't want to pick wildly different domains for these functions because they're the reciprocals of sine and cosine. So what's a cosecant look like? It looks like this. So we've got one branch here, and we've got one branch here, right? Because sine goes through 0 at 0. It's negative to the left of 0, it's positive to the right of 0, so there's infinite discontinuity there. And we have an asymptote, and of course, you know, there's more branches to the right and to the left. And so this is the cosecant function, right? So 1 over the sine function. And so we're actually going to restrict it to the exact same domain. We're going to restrict it from negative pi over 2 to pi over 2. Because if you take a look, this is going to start here, and it's going to shoot down to negative infinity, and then there's this gap of length 2 from -1 to 1 that the function doesn't have in its range, and then it's coming down from positive infinity and stopping at a height of 1 at pi over 2. And so there's clearly no going back up over there or going back down over there, so if we restrict to the domain in this way, there will be no failure of the horizontal line test. So we're just literally keeping like this weird gap in between, but this is how it's defined, in sort of keeping in mind the smallest angle and passing the horizontal line test. So reflecting it across y equals x is pretty convenient. It just looks like this. So we invert it, and we end up with these two branches that approach the x-axis as an asymptote very, very rather quickly. Not quickly enough that the area under it is finite, though. But essentially, it's flipped the domain and range again, right? This gap that was -1 to 1 in the y-axis is now -1 to 1 in the x-axis, and it simply keeps the inverse well-defined. Likewise, the secant function is going to be over 0 to pi, just like the sine function. Just like the cosine function, which is, and remember, secant is 1 over cosine, and so we're going to end up with the two branches sitting above, right, going from 0 to pi, and essentially they will look like that. So they will have these points that sort of jut out and stop, just like the inverse cosecant. So this goes up to pi, right, and this is still -1 in the x direction, and this is still 1 in the x direction and going to 0 instead. So it all sort of fits together. If you look at the graphs of the cosecant and secant functions in their regular configuration, you'll see this exact relationship just reflected over y equals x. So both of these are, so this one is the arc secant, so inverse secant or arc secant of x, and this one down here is the inverse cosecant or arc cosecant of x. All right, so one more pair of functions, and that's the tangent and cotangent. So if we take a look at the xy plane again, I'm just going to only draw the one branch of the tangent function because it's actually pretty clear right off the bat that that's all we're going to need, because it goes from negative pi over 2 to pi over 2, and it goes from negative infinity to positive infinity, and these are both asymptotes of the function. So just as soon as it starts coming up from negative infinity here, it's already violated the horizontal line test infinitely many times in the lower axis. And anytime it starts coming down from positive infinity here, it's already violated the horizontal line test infinitely many times in the upper part of the plane. So it seems clear that we just want to restrict it to this one branch of the tangent function, which is absolutely correct, because it's strictly increasing, which means it never goes back down, and it's over a finite interval. So we can just reflect it, and we end up with the very nice looking arctangent function. And I'm just going to erase the tangent function now. Naturally, the domain and range have flipped, so we go from negative pi over 2 in the y direction to pi over 2 in the y direction. Again, these are horizontal asymptotes of the function. They will never get to these numbers. You simply have to take the limit as x goes to positive or negative infinity to have that as a valid answer. This wasn't drawn that close, but essentially it's just a horizontal asymptote. And cotangent is very similar, right? But again, in tangent, the numerator is sine, and we're going from negative pi over 2 to pi over 2. And in cotangent, the numerator is cosine, and we're going from 0 to pi over 2. So I think there's probably a relationship, right? And the inverse sine and cosine, not the reciprocal sine and cosine functions also had the same respective domain restrictions. But essentially what's going to happen with the cotangent function is not much different. So it's going to go from 0 to pi, right? Not too surprising there, right? And it's going to go like that. And this is at pi. Right, so that's at pi right there. And so the restriction of the cotangent is from 0 to pi, and so we invert it, and then we end up with this right here. And so these are the inverse functions for the cotangent function, so inverse cotangent or arc cotangent of x, and the orange one is the inverse tangent or arc tangent of x. All of these inverse functions simply tell you the angle that gave you the trigonometric answer. So if you know that the sine of 60 degrees is root 3 over 2, then that means that the arc sine of root 3 over 2 is 60 degrees, or pi over 3 radians, since we're all adults. So these simply just give you back the angle that gave you the trigonometric value that you started with these restricted domains. If you go outside of those domains, it's not going to be well defined unless you want to pick that specific branch cut. And that's a whole nother deal, right? But usually, and what calculators run on, is these restricted domains of the functions, because it's the most convenient way to just keep it well defined and not doing any multi-valued functions, which is again another, more or less the same topic I just mentioned before with branch cuts. There's a neat little relationship between these that I want to mention. So now that you've seen all the functions and why they're restricted in that way, much like how 1 over the sine of theta is equal to the cosecant of theta, we also have that sine, the inverse sine of 1 over x is equal to the inverse cosecant of x. So the input is if the input is reciprocated inside the inverse trig function, you get the inverse function of the reciprocal of the regular function here. So likewise, if you have 1 over the cosine, so that's one thing, and there's 1 over the cosine, and that's the secant function, it's the same thing, right? Cosine of 1 over x is equal to, inverse cosine of 1 over x is equal to the inverse secant of x. So the reciprocal input is what causes the change. The same goes for tangent and cotangent, right? So they're pretty interesting functions. In the next part of this series, I'm going to do graphing and understanding the domains and ranges of the hyperbolic functions. And then after that, I'm going to do a video on understanding the domains and range of the inverse hyperbolic functions. And then following from that, we're actually finally going to really dig into the hyperbolic functions. I just wanted it to be clear how these things are related, and I wanted to finish up this little series. Also, I'm going to be deriving at least the first few of the complex logarithm versions of the inverse trig functions, and then another video on the regular log versions of the inverse hyperbolic functions. So I've got a lot to cover. I know I'd like to dig into more hyperbolic function stuff, and so that's exactly what I'm going to do. I just need to, like, tie up some loose ends, you know? I feel like I want to have the stuff that I'm going to use as part of the videos on my channel. Thank you very much for watching. Stay tuned for the next, you know, thing. Bye-bye. This channel has an Instagram, so it is at @WhatTheHectagon, of course, and it has a Twitter also. So this is Instagram, and of course this is Twitter, and it is of course naturally, also WhatTheHectagon, at WhatTheHectagon. Nope, at the Hectagon. Oh, can't spell today. Okay, Hectagon, and my email is the incorrectly spelled WhatTheHectagon. Why spell check before you make the email right, that you can't then change, at gmail.com. Now all of these are in the description if you don't want to have to somehow watch the video and pause it and actually write it down, along with other Instagram, Twitter, YouTube accounts that me and my friend Bill run. He does one for D&D. We together stream on Mixer under the moniker of Fredwood Live. So check the description for other stuff. This is just for my channel. This is my Instagram, at WhatTheHectagon, Twitter, at WhatTheHectagon, and email, at WhatTheHectagon, because I spelled it wrong when I made the email and now I can't change it. So that's the stuff. Thank you for watching, and bye-bye.